what about when we're not under standard conditions, as most reactions are? If we change the concentration of the reactants and products so they're not 1 molar, that's going to affect our free energy change and our equilibrium constant. And because our free energy change determines our cell potential is going to be different when the ion concentrations aren't 1 molar. So for example here, we've looked at this reaction multiple times, but if we change our concentrations, lower our zinc, so essentially we're shifting this reaction to the right, and then we increase our copper concentration, so we're also shifting this one to the right, we can increase our cell potential under non-standard conditions. Now the way we do that is we learned this equation in the previous chapter, and then so we can substitute in delta G is negative NFE, substitute that in plus RT natural log of Q. So this is our cell potential in the cell we're using. This is the standard cell potential. Kind of rearrange things, and we can get this equation, which is the Nernst equation. If our temperature is 25 degrees Celsius, we can use this version, where our potential is the potential under standard conditions minus 0.0592 divided by N, again that number of electrons, log of Q. So let's work through an example of that. Calculate the cell potential at 25 degrees for the reaction given there. We're given our reaction and these concentrations. So from the previous slide, we know that our cell potential, cell potential is the cell potential under standard conditions minus 0.0592 over N log of Q. Then our Q in this case is going to be our products, which is in our common state, so just our aqueous ones. So our concentration of copper divided by our concentration of manganese squared times our concentration of H plus to the 8th power. That's our Q value. So we need to find our standard cell. We can look up our values in the table. We've gone over how to do that several times. So our overall cell here is going to be our cell potential under standard conditions is going to be 1.34 volts. And again, that's just from the numbers in table 18.1 minus 0.0592 divided by N, which is our number of electrons. And again, if you look it up, we are doing the copper to copper 2 transfers 2 electrons, but there are 3 of them. There should be a 3 right here as well. So this is going to have to be cubed. Sorry, there's a typo in my slide. So divided by 6, because 3 transferring 2 electrons 3 times gets me 6 electrons, times the log, and then we can plug in our values. It's going to be 0.010 cubed divided by 2 to the 2nd and 1 to the 8th. So if you do all of that math, we are going to get a cell potential of 1.41 volts. So there we go. and our cell potential is greater because of the way we're shifting things. Next question. Similar thing, so I would recommend pausing and working it through yourself first. Calculate the cell potential for the reaction at 25 degrees Celsius if all ion concentrations are 0.1 molar. This is that same reaction we've looked at multiple times. So we have our 1.2 and our 0.54. So my standard cell potential is 0.66 volts, and I am transferring 10 electrons. And I know that my new cell potential is my standard cell potential minus 0.0592 divided by n log of Q. And my Q in this case, let me write the rest of this down again, is 0.66 minus 0.0592 over 10 log. And my Q is going to be, oh, sorry, I need to start with my products. I don't have any products in the common phase, so I'm just going to put a 1 up there. And then my reactants are, for the IO3 minus, 0.1 squared. For the H plus, it's going to be 0.1 to the 12th. And then my I minus is 0.1 to the 10th power. So my new cell potential is 0.52 volts. So I've lowered all of these concentrations. Instead of being at standard condition, they're 1 molar. So it makes sense that my cell potential is lower because I'm starting with less material. All right. We can create a voltaic cell based on concentration instead of having two completely different reactions going on. So if our cell concentrations here are equal, there's not going to be any change in potential. But if we have a situation where we have a low concentration on our anode side and a high concentration on our cathode side, we're going to get flow because our solution here, we're going to be driving it this way to make more copper, 2+, and here we're going to be driving it in the opposite way. And so we will end up with a current under non-standard conditions. Some batteries take advantage of things like this. So your basic alkaline dry cell has an alkaline potassium hydroxide paste. The anode is zinc or magnesium. Cathode is a graphite or brass rod, and we're just reducing manganese for oxide. And if you look at this reaction, look up the numbers. The cell voltage is 1.54 volts, and they have a nice long shelf life, rechargeable, not a lot of corrosion associated with them. This is comparing them to acidic dry cells, which are not generally commercially available. One other battery I wanted to point out uses this kind of chemistry. Actually, all batteries use this kind of chemistry, but we're going to talk about the lithium-ion battery, which uses potassium hydroxide solution. The anode is graphite with lithium ions. Lithium is nice and lightweight. And the cathode is a kind of complex lithium transition metal oxide. And so the electrons will move from the anode to the cathode. These have the advantage of being very light and have a long shelf life, and they're more environmentally friendly. Fuel cells is another application of this chemistry. They're like batteries, but you're constantly adding in reactants so they don't run down. And then you have platinum electrodes, but you're reacting hydroxide and hydrogen to form water for your product. And you can get a current out of that.